Today's experimental mathematics speaker is the one and only my co-organizer, Robert Dougherty-Bliss, who will talk about Gosper's algorithm and Bell numbers. As usual, please unmute yourself unless you have something to say. But otherwise, you're welcome to interrupt every second. Thank you.
Well, thank you for the introduction, Dr. Z. I appreciate it. Glad to be here again with everyone. Let's see if I can get this. There we are. There we are. Okay. So yeah, today I want to talk a little bit about Gosper's algorithm and Bell numbers. But first I want to say one thing that's really great about being here at Rutgers is actually that we have the experimental math seminar, because we have so many people that know so many things about sequences. So this is great and also sometimes horrifying, because you can't ever say anything without someone in the audience knowing exactly what you're talking about. I think I've never given a talk with a sequence in it where I didn't see Neil somehow nodding and mouthing the A number to the sequence I was talking about. So I wanted to start by having a little guessing game to test and make sure everyone's still on the top of their game. So I have 4 sequences here that I think that the experts in the room hopefully can guess at least 3 out of 4. We'll see.
Are you allowed to cheat and copy and paste it? Or that's...
No cheating. You have to know off the top of your head. So you can play along in your head, or you can yell out loud. Anyone know the first one?
N factorial.
Okay. In factorial. That one's too easy. How about the second one?
To the power minus 1.
Okay, also too easy. How about the third one?
Bell, rings a bell.
Yeah, those are the Bell numbers. But how about the fourth one?
No clue.
While I'm waiting, by the way, if you don't know, the third one, the Bell numbers, that's the number of ways to partition a set of n objects into non-empty parts. But how about the fourth one? Anyone recognize this?
The Robert Dougherty-Bliss numbers.
No, unfortunately, I can't steal the honor. These are called the Gould numbers.
Oh.
I'll give you the definition a little bit later. It's a sequence that came up when studying a certain binomial transformation. But try and remember some of those numbers. 1, 1, 3, 9, 31. These...
Well, actually, if you look at the powers of 2, you've got 2 to the 1 plus 1, 2 to the 3. So the powers of 2 are 2, 3, 5, 7, and 9. Okay, that's one we can generalize in infinitely many ways.
Yeah. But so we'll talk more about these numbers a little bit later on, I guess. The Gould numbers are in the OAAS, so we'll see it soon. Okay, now that's enough for sequences. You can also play this guessing game with sums. We've got a lot of summation experts here. Some of these are too easy. Like you can sum up powers of 2. Okay, you get powers of 2. We know that. You can sum up Fibonacci numbers. Any undergrad could tell you that you get Fibonacci numbers back. But what if you sum up reciprocals of factorials? This is also an easy one.
Harmonic.
No, this is not reciprocals of integers. This is reciprocals of factorials.
That's the simplest possible indefinite sum that cannot be expressed in closed form according to Gosper.
Yeah, okay. So this is bonus points for answering the trick question. Not every sum has a closed form answer. Unfortunately, there are some sums that can't be done. Of course, the sum of the reciprocals of factorials, it kind of is itself the answer to the sum, but there's nothing you can really write on the right-hand side that's much better than that. Maybe there's some expression in terms of, more complicated things, but you're not going to get something better than essentially the sum itself, which is just kind of an unfortunate fact about certain sums. However, you can fix certain sums, even if they don't work. So for example, 1 over k factorial, you can't sum that, but take a look at this sum, k minus 1 over k factorial. This one you can do, and it's not even that hard to do. If you distribute the k factorial, you get 1 over k minus 1 factorial minus 1 over k factorial, and this is telescoping, so it's just right away, you're done. That's easy enough. But I would dare you to try and come up with a quick proof for the next 4 sums here that look like this. So here are 4 different tweaks, or 5 different tweaks to 1 over k factorial that takes a sum that doesn't have an answer and turns it into something that does have an answer. Now, I guess once you know the answer, it's kind of easy to go back and prove it by induction, but the trick would be, could you figure out the answer before you know induction? Or before you know the answer, could you prove it without the answer using induction or something like that? And what's kind of interesting here is take a look at the pattern of what's going on. Each of these sums is of the form some monomial minus a constant. And those constants are 1, 2, 5, 15, and 52. Does that ring a bell to anyone?
Joke.
Right, so these are the Bell numbers again. So what I want to do is I want to try and explain a little bit what's going on here. Like, what is happening? Why are these Bell numbers appearing? Why do we get these closed form answers with monomial minus a constant over k factorial with the Bell numbers and not other numbers? And to do that, I need to explain a little bit about what we mean when we talk about an answer. And to do that,
and Robert, it's probably if and only if, right?
it is if and only if.
Yeah.
These are these constants work, and only these constants work, actually. You can't replace this 15 with any other number and have this have a closed form answer. Only 15 works there, and only 52 works here.
Yeah, otherwise the sum of reciprocals of k factorial will be in closed form.
Exactly right, exactly right. So to try and explain a little bit more about why these Bell numbers are cropping up, I need to explain a little bit about what we mean when we say an answer. And to explain that, I need to talk about Gosper's algorithm and hypergeometric summation. So when someone says an answer, when they're talking about a sum, they normally mean a closed form answer. And this is a familiar idea, even if you're teaching like calculus students when they're trying to do an integral. Normally, you don't just want the indefinite integral, but you want some kind of elementary antiderivative. So here we want something similar. We want our sums not to just be written in terms of the indefinite sum itself, but actually some closed form expression. And in the context of summation, when someone says closed form, they almost always mean, to say 80% of the time, something about hypergeometric. What hypergeometric means is you take a sequence and you look at its consecutive ratios. So if f of n is your sequence, you're looking at f of n plus 1 divided by f of n. You're hypergeometric if this is a rational function in n. And this definition covers a pretty broad class of sequences. It covers polynomials, rational functions, exponentials, factorials, and then any products and quotients of those, which is the majority of things you're going to run into in combinatorics and counting problems, things like that. So the question is, if I start off with something that's hypergeometric, like a closed form expression, when is the sum, the partial sums of that hypergeometric? When can I turn my indefinite summation into something concrete in a closed form? And this question was answered back in the 1970s, I think, by Bill Gosper. He produced this algorithm that just completely answers the question. So what the algorithm takes in is some explicit hypergeometric function, f, or some hypergeometric sequence, and what it spits back out is either an explicit antidifference, so an explicit hypergeometric function that will work, like it is the part equal to the partial sums of your sequence, or a proof that no such hypergeometric function exists. So it's actually a decision algorithm. It tells you, yes, there's an answer, and here it is, or no, no answer exists, which just completely solves the whole problem right there. Now, the way that Gosper's algorithm works is you try and reduce the problem step by step. At first glance, it's a little difficult to try and find hypergeometric antidifferences because hypergeometric functions is a pretty broad class of functions. So what you want to do is break it down step by step into smaller parts. The first step is actually kind of straightforward. It's a very pretty fact. You may or may not know this, actually. If you have a sum and it turns out that there's a closed form answer, like a hypergeometric answer, then the answer is always a rational function times your summand. Restated this way here, if I have some hypergeometric function that when you take the difference gives me f, so this would be the partial sum of f, then s has to be a rational function times my summand times f. And this fact is not so hard to prove. If you factor out an Sn from that equation at the top there and then divide through by the resulting factor, you get that Sn is something times f, and that something has to be a rational function if you assume that these consecutive quotients are rational. And this right away reduces the problem. Now you're no longer looking at all possible hypergeometric functions, but you're looking at very specific ones. Your summand times a rational function, which is easier, but it doesn't completely solve the problem. The next thing that you have to do in this reduction is try and reduce down to polynomials rather than rational functions. And the exact reduction is a little complicated, but I want to give you some sketch of the idea so we have something to hold on to moving forward. The exact structure of the reduction here looks something like this. If you have a hypergeometric term, you can normally think of it as two different parts. There's a pure part and a polynomial part. The rough sketch of how it works. The pure part is the part that when you look at these quotients, something cancels, something significant cancels. For example, if you look at the quotient of n factorial, you get n plus 1 factorial over n factorial. A bunch of things cancel there, and you get something nice and rational. That's like the pure hypergeometric part. And then sometimes you have other stuff that doesn't cancel, but it's kind of rational by default. For example, if you had like a polynomial factor out front, it doesn't stop you from being rational, but nothing particularly cancels nicely either. So when you look at a hypergeometric part, you break it into two things, the polynomial part and the pure part. In this case, we've got n minus 3 times n factorial over 2 to the n. If you look at the consecutive quotients, the n factorials cancel nicely, the 2 to the n's cancel nicely, and this polynomial part doesn't really cancel at all, but it's still rational. So it's fine. You're still hypergeometric, but nothing particularly nice happens in the quotient. So when we talk about these hypergeometric parts, these are the two parts that we're going to decompose things into. Now, when you look at this quotient, what you want to do is imagine that you had decomposed your term into this pure and polynomial part. So you look at your consecutive quotients and you say, there's an a over b, a rational thing out front that came from my pure parts canceling. And then there's also some polynomial part where I had some polynomial and whatever, the rational function I got there was just the shift of a polynomial over itself. And that's the decomposition. The exact idea is a little more technical. There needs to be some restrictions on a and b involving some things need to be relatively prime, but for now, this is good enough to understand. And what Gosper's algorithm really amounts to is this statement right here, that there is a hypergeometric antidifference for your sum, if and only if there's a polynomial solution to this equation right here, where this equation is something induced by the decomposition of your consecutive quotients. So some linear combination of these x's, where one is multiplied by the numerator, one's multiplied by the denominator, needs to equal your polynomial part. And in that case, there's actually, you can just write down, this is the sum. The sum is denominator divided by polynomial part times whatever the solution to this thing is. And what's really swell about this is you've reduced the problem all the way from hypergeometric functions down to polynomials. And in fact, this equation is very easy to solve if you fix this a, b, and c. Because if I give you sort of a fixed hypergeometric term, you can give me back a, b, and c, and you can plug in a generic polynomial for x and then use undetermined coefficients to try and solve for what that polynomial has to be. And this turns out to be a very effective procedure. You can even work out bounds for the degree on x, like x can't be bigger than degree 7, degree 10, whatever it happens to be. And that way you just plug in a sufficiently big generic polynomial, set up undetermined coefficients, solve some system of linear equations, or realize that it doesn't have a solution, spit out the sum, or spit out a proof that there is no sum, or no hypergeometric sum. And that is basically the gist of Gosper's equation. There's some sweat involved in proving that you can reduce down to this step, but otherwise, that's the whole idea right there. So what you would do is you take this, you plug in your sum being, say, 1 over k factorial, that's your summand. You would get down to this step, and then you would look at it and say, oh, there's no polynomial solution, so there's no sum, and you'd be done. But there are lots of other interesting ways that you can apply Gosper's algorithm. The normal way is what I just said. You give me a fixed term, and then fill in these details, fill in the a, fill in the b, fill in the c, and then you try and find some solution to this equation. But another way would be something more like this. So imagine someone asked you, when is the sequence polynomial times n factorial summable? That is, when does this have a closed form answer? For which polynomials does this have a closed form answer? If you go through the details of Gosper's algorithm, you'll see that you can't sum up the factorials by themselves. So a constant polynomial doesn't work. But it's not even that hard to see that n times n factorial does work. You could probably give that to like a smart undergrad in intro to proofs and they could figure it out. So you cannot sum up 1 times n factorial, but you can sum up n times n factorial. So the question is, which polynomials make this summable and which of them don't? And you can use Gosper's algorithm to answer these kinds of questions, this style of question. And how it would work is you take this term here, this f, you say, fine, f is some polynomial times n factorial, and you look at these consecutive quotients. When you look at the consecutive quotient, you see right away how to decompose it into pure and polynomial parts. Even looking at it here, you can kind of see the pure part is going to be n factorial, and the polynomial part is going to be whatever polynomial that you plugged in. And in this case, sure enough, the numerator of the pure fraction is n plus 1, the denominator is 1, and then the polynomial part is just whatever polynomial that we plugged in. So Gosper's algorithm tells you then that this hypergeometric term will be summable, has a closed form sum exactly when P lies in this vector space right here. Exactly when P can be written as a linear combination of some input polynomial where the coefficients are n plus 1 and then a constant 1. And what's nice about this description now is that this is a linear map in this polynomial x. So if you want to get a basis for this, you can just plug in basis polynomials. You can plug in, say, monomials, powers of n, n squared, n cubed, things like that. And if you do that, you can actually work out that a nice pretty form of the basis looks like this. The basis starts n squared plus 1, n cubed minus 1, and it goes on and so forth like that. So the polynomials that make n factorial summable are exactly linear combinations of these polynomials here, where you can keep cranking out terms as much as you want.
What comes after n cubed minus 1? What's the next term in that list?
I think it might be n to the 4th plus 2.
Okay.
I think it's n to the 4th plus 2.
Okay, thank you.
In fact, I think the Bell numbers pop up here. I think they might be alternating Bell numbers. So yeah, you can work out this basis and you can crank out as many terms as you want. It's very effective. You can write a little maple code to do this. That's why n times n factorial works. But for example, n squared times n factorial does not work. But n squared plus 1 times n factorial works. So this would be a neat problem, maybe a cool problem to give to some, aspiring discrete math student in undergrad. Okay, so the gist of what I just said is that if you have a pure hypergeometric term, then there's a vector space of good polynomial parts. You write down any hypergeometric term, any pure hypergeometric term you want, like k factorial, 1 over k factorial, and I can produce a vector space of polynomial parts where the sums then will have good answers. They'll have closed form answers. So take a look at the sums that we saw from earlier again. These are the sums, some monomial minus a constant over k factorial. So k minus 1 over k factorial, k squared minus 2 over k factorial. And I said that these were the ones that had the nice closed form answers. With this idea in mind, these polynomials, k minus 1, k squared minus 2, k to the cube, k cubed minus 5, and so on, this forms a basis for the good polynomial parts for 1 over k factorial. So the problem of explaining why the Bell numbers cropped up here really comes down to, can you explain how to get a nice, pretty basis for these good polynomial parts? I'll write down some explicit vector space, and you try and give me a pretty basis, something that looks like this, and try and explain somehow why the Bell numbers come out of that basis. So that's the trick now. We need to construct a basis and find a way to turn it into something pretty where the Bell numbers appear. So how do you get the basis? Where does the basis come from? Well, like I said, it turns out that this is some vector space determined by a linear map. So you can get some basis by plugging in linearly independent polynomials. An easy way to do it is just plug in powers of n. If you plug in powers of n into Gosper's equation, then you'll end up getting a basis that works. In this case, if you plug in powers of n with a minus sign to make everything look pretty, here are the first few terms of the basis that you get. So the basis we're looking at is n to some power minus n plus 1 to the previous power. So these are some of the basis polynomials that will work. But you'll notice that the constants are not quite right. The basis that we had up here it was only monomial and then constant, and no intermediate terms. But here we have a lot of intermediate terms. If we start off with n squared, we've got an n. We start off with n cubed, we've got an n squared and a 2n. So the game here is, can you start off with this easy basis that you get from Gosper's equation and somehow eliminate these intermediate terms? And of course you can, just by doing some linear algebra, just working out the right combinations. So you start off with the initial one. If you take the first one and you add it to the second one, that cancels the linear term. If you take the last one, you add the previous one, and then 3 times the one before that, that cancels both the quadratic and the linear term. And you end up getting the constants 1, 2, and 5, which are the first 3 Bell numbers, or maybe the second, third, and fourth Bell number, depending on how you're counting. So this is the game that you play. You start off with this basis here that you get easily using Gosper's equation, and then you want to turn it into some prettier basis, some simplified basis where you cancel the intermediate terms. And you can do that by cooking up some big, giant, infinite change of basis matrix that looks like this. So on the right-hand side, here are the basis elements that you get from Gosper's equation, the easy basis. It's easy to write this basis down. And what you want to do is turn it into the basis elements on the left-hand side, where you've canceled all the intermediate terms. And how you do that is multiplying by this big change of basis matrix, which tells you the correct combinations that you need of the things on the right to cancel to get the things on the left. Now, what's really swell is that you can figure out this matrix all automatically. You can just guess the entries of this matrix. You can also write down exactly what it is. It's not too hard to examine the change of basis equation and come up with an equation for it. But what's cool is that this matrix turns out to be in the OAIS. Oh, for now, I should mention, this also kind of explains where the Bell numbers come from. So you see 15 here. This is the sum of 9, 4, 1, and 1. The constants that you get on the left-hand side are actually the row sums of this matrix right here. And if you sit down and think about it, it's not too hard to see that, because the constants on the right-hand side of these basis elements are all 1 with a minus sign. So the constants you're going to get here are just whatever multiples that you see here added together. So 52, 31 plus 14 plus 5 plus 1 plus 1. So hidden in this matrix somewhere is some identity that says the sum of some rows of some famous matrix ought to be the Bell numbers. That's how you would explain where they come from. Now, this matrix is actually well known. People have studied it before. Henry Gould and I think Jocelyn is the first name, Jocelyn Quaidnant, studied this matrix back in 2007. They were studying it in relation to certain binomial recurrences, I think, transformations of binomial sequences, and writing down some generating functions and identities and things like that. There wasn't anything particularly relevant to sums or even counting in there, really. It was just thinking about different binomial transformations. But even with their paper, without their paper, you can sit down and write down a definition for their matrix. It looks like this. It's got 1s on the diagonal, on the principal diagonal. And then after that, each column is something like the binomial transform of the terms in the column before it. Something like that is how you could put this into words. But in any event, there's a formula right here. And what's neat about this formula is if you just sum across the rows now at this point, it tells you that the row sums satisfy a really neat binomial recurrence, and it's actually the exact defining recurrence for the Bell numbers. So if you just sum over j here on both sides, you just swap the order of summation, and you end up getting that the d plus 1 sum is, the binomial transform of the sums before it, more or less. And this is the recurrence that defines the Bell numbers. So as long as the first Bell number showed up, all of the remaining Bell numbers would show up then immediately after that.
This Bell, of course, is Eric Temple Bell, right? So it should be a capital B.
Yeah, I suppose you're right. Maybe it should be a capital B, at least here. At least this B should
in the last line, yeah.
Yeah, definitely. Maybe you're right. Yeah.
Men of Mathematics, he wrote.
You're right.
I don't know. A billion groups, you don't capital A. I think it's a big honor not to have it capitalized. I mean, it's so.
Fair enough.
Robert, go ahead. I can hear you. Robert, are you speaking?
We can't hear you at all.
How about now?
Okay.
Much better.
Okay, good. Anyway, okay, what I was saying is that maybe I'm not capitalizing Bell because I think it might be lowercase in generating functionology. Maybe in Wilf's book it's not capitalized. I can't remember. So I'll plead the Wilf defense, I suppose, in this case. Maybe it should be capitalized though. So by the way, oh, I just gave it away. Darn, I was going to ask. Does anyone recognize the first column there?
That's the Gould numbers you mentioned before, right?
Yes, those are the Gould numbers. I hope you didn't see the slide, otherwise you're cheating. So those are the Gould numbers, that first column. There doesn't seem to be any particular significance to this problem except for the fact that the Gould numbers showed up here. Now, like I said, the definition of the Gould numbers originally, was almost literally, it's the first column of this matrix that they were studying in relation to some binomial transformations. But it turns out that there's a couple equivalent ways to define the Gould numbers. One is that the Gould numbers have this exponential generating function, which is a really amazing generating function, I have to say. This right here, this first factor, that's the generating function for the Bell numbers. And this integral right here is related to some well-known stuff, but I don't know what to call it off the top of my head. But this is, a really astounding generating function. It's very fun to compute some terms using this idea here. You have to expand this generating function, which is well known, and then integrate by term by term. And it turns out there's even a combinatorial interpretation for the Gould numbers, where A of n is the number of partitions of 1 through n, where the last block is a singleton, and you arrange the blocks in order of their least element. So in this case, to see that A of 3 is 3, look at all the permutations or partitions of 1 up through 3, where the last block is a singleton. So one way to do it is just have them all be singletons, and the last block's a singleton. Have 1 and 2 be together and split 3 off by itself, and have 1 and 3 be together and split 2 off by itself. And in this case, 3 comes last because it's bigger than 1. In this case, 2 comes last because it's bigger than 1. So it turns out that the Gould numbers count this. And they also happen to count a certain number of permutations that avoid a pattern, but I won't get into that. But they also have some significance there in pattern avoidance. Now, something that's kind of interesting about the Gould numbers is that 1 Gould is roughly 0.6 of 1 Bell, it turns out. So there was this conjecture in Gould and Quaidant's paper that asymptotically, the Gould numbers divided by Bell numbers turns out to be 0.6. It's not 0.6, it's this integral right here, which is called the Gompertz constant, which is some constant that has significance in a couple of different problems, but it's some convergent integral. It's actually 0.59, something like that. And it was proved later by Asakli and some friends, including a former speaker at the seminar, Tufik Mansour, was also on that paper. And he helped prove that. Some very neat complex analysis tricks in there. So if you ever wanted to know, just by chance, if someone asked you, roughly of all the permutations of 1 through n, how many of them, if you arrange them in order of their least element, have the last block be a singleton? Now you know it's about 60% of them. So that's a neat little trick.
Is it a probabilistic explanation? Because Gompertz was a famous combinatorialist and actuary, and I guess the number came up first in probability or in statistics. So I wonder if there's any intuitive connection between the original meaning of Gompertz constant, whatever it is, and this particular limit.
Yeah, that's a good question. It might be worth digging through the proof, which does, or actually, it might even be worth going back and reading Gould's original paper, which has some motivation for the conjecture, which I think might be a little more revealing than the proof itself, which does some complex analysis. So maybe if you go back and read
the paper from 200 years ago, probably.
Yeah, maybe there's something there that would be worth looking at. Yeah, that's a neat idea. I mean, there's clearly some probabilistic interpretation here. You randomly sample, what's the, anyway, maybe there's something more significant though than the dumb interpretation. There are a couple other interesting combinatorial things that fall out of this example here. So what you can do is, if you have this change of basis matrix, if you remember, there was this big long list of summation identities where it said, okay, there's this closed form if you have this Bell number thing on the left-hand side, but then on the right-hand side was just some disgusting polynomial divided by a factorial. And the question is, how do you actually figure out what that polynomial is? Like, fine, this sum has an answer on the left, but what is the answer? Well, using the change of basis matrix, you can actually write down what the answer is. It's not super satisfying because it involves, rows of this very complicated matrix that's defined recursively, but you can write it down. And what's more, because of this identity, this is an identity, a summation identity involving a fixed Bell number, which means that if you actually stick some bounds on these sums and rearrange things, this implies an identity about the Bell numbers. And that identity is this right here. So the identity says that for any Bell number you want, B of D is equal to some very complicated fraction involving some sums and powers and rows of this matrix that we talked about before that ostensibly depends on n in some way, where n is an arbitrary parameter. And what's interesting is this reminds me a little bit of the infinite series expression for the Bell numbers. I wonder what happens if you take a look at this quotient here and you let n go to infinity, if you recover anything that's like the infinite series formula for the Bell numbers, which is of course not super helpful in computing them, but kind of a neat novelty. But in any event, there's this Bell number identity here that seems to be like crying out for some combinatorial interpretation. Maybe you can think of this probabilistically, maybe you can find some counting argument by moving things around. I'm not entirely sure, but it seems like there's something going on here that I don't really understand that falls out by accident when I'm thinking about this summation identity right here. But anyway, let's recap where we were. So what we were saying is that this sum right here, the sum of monomial minus Bell number, or monomial minus constant over k factorial, this is only solvable in closed form, only can be expressed as a closed form if that constant is a Bell number, and the Bell number that corresponds to the monomial. That's it. There's no other way to do it. And we got this by playing around with Gosper's equation, plugging things in, getting a basis, simplifying it using some linear algebra. And as you might expect, you can do all of this with slightly more complicated hypergeometric terms. It isn't just 1 over k factorial where this works. And the general statement looks something like this. The different ways that you can generalize this is you can take the k factorial and you can replace it with a rising factorial or a Pockhammer symbol. So that's a times a plus 1 times a plus 2 all the way up to a plus k minus 1. And you can also introduce an exponential factor there. So in the top, we've got a equal to 1, z equal to 1, and this will recover the Bell number result. In general, the answer is you'll have monomial minus a constant, and this will have a closed form expression. The sum will have a closed form expression, provided that this constant is the coefficient on some power of x and this exponential generating function. The way that you get this is you write down the basis from Gosper's equation, you do some manipulations, and you can work out some differential equations that these generating functions have to satisfy, and they turn out, we get lucky, we get a nice closed form solution in this case. And if you let a equal 1 and z equal 1, this actually recovers the generating function for the Bell numbers. So that, again, explains where the Bell numbers come from. And what's better is actually this generating function right here is directly related to the Bell numbers in some kind of nice way. If you let big B of x be the generating function for the Bell numbers, then this generating function for these constants that make the sum work is actually Bell numbers raised to a power times some exponential function, which says that there's an interpretation here. It says something like these constants are the binomial convolution of the Bell numbers with themselves a number of times and then with powers of 1 minus a, which is really too disgusting to think about in any reasonable way. But as long as you set the parameters to be something small, you get something nice and reasonable. For instance, if z is 1 and a is 1, it just says you get the Bell numbers. But for instance, if you let z be 2 and a equal 1, then this tells you something about these sums right here. you want to look at monomials minus a constant times 2 to the k over k factorial. So you want to know, when does this have an answer? When does it have a closed form? And the answer is if and only if this constant turns out to be a convolution of the Bell numbers with themselves. So these are the only constants that work. No other constants will make this sum have a closed form. And then by setting z to be, 3, 4, 5, by letting a be, instead of an integer, letting it be, say, a half or 3/4, things like that, you can get related identities involving more and more complicated sums here. Now, the reason that this all works, kind of big picture, is that if you go all the way back to Gosper's equation, that vector space has a basis where the powers start at 1 and go up by 1 at every step. They go 1, 2, 3, 4, and so on. If you wanted to broaden out to slightly more complicated things, you could do that. The trouble is that as your hypergeometric terms get more complicated, you get more complicated vector spaces, and you won't be able to cancel down the constants the way that we did here. You'll have to accept that it will be, monomial minus linear term minus constant, or maybe monomial minus quadratic minus linear term minus constant. So you'll be able to get something similar to what we did here, just not quite as pretty, not as I think striking as monomial minus constant like we did, but it's definitely possible. The next easiest thing would be to just do monomial minus constant times k factorial. Then that gets you things there. That's also fine. So the summary here, the idea of everything that we did is you can take Gosper's algorithm, you can look at some bad sums like 1 over k factorial, and you can make them good just by sort of playing around and trying some automated guessing stuff. Once you make them good, you can find neat patterns in all of this stuff, and then you can turn Gosper's algorithm on its head. And instead of using it as a tool to check when something is summable, you can use it as a tool to prove when an infinite family of sums has an answer. And then based on that, you can find lots of neat combinatorial numbers and patterns and conjectures and formulas that demand some explaining. But I think that this is a very neat application of Gosper's algorithm to a cute sequence of problems. So I suppose I will stop here a few minutes early.
Thanks. We have plenty of time for questions. This is really beautiful, combining Gosper's algorithm with combinatorially significant sequences. Any questions for Robert?
Robert,
Yeah, Stoyan?
can you go back to the previous slide, 18?
This one.
Yes. So you're saying these sums have closed form only in this case. Is the actual closed form nice here for?
Well, so the closed form will turn out to be some polynomial times 2 to the n over n factorial.
Okay.
It's not a particularly nice closed form. No, I don't think so.
Okay. Yeah.
Did you try some other kernels, for example, k factorial square at the bottom?
Yeah, so the problem with k factorial squared is you run into this issue where the basis, let's see if we can go back to here. So in this case, when you have 1 over k factorial, the basis starts off with a linear polynomial. But when you get 1 over k factorial squared, the basis starts off with a quadratic polynomial, and the cancellation gets to be not quite as pretty. So you can do it, but now the basis that you get when you simplify it won't be as striking as this here. So I do have some examples of that, but I didn't bother to write them up and put them in the slides.
Oh, so you get something, but not as nice.
You do get something, yes.
Yeah, I have actually a very naive question. So in terms of searching for a closed formula, so you gave a definition, but then of course there's also n factorial is allowed in the final formula. Right now, n factorial, of course, is the product equivalent of having a sum that goes from 1 to n, right? And so there's no shortcut for that. So why is that considered a closed formula if sum of going all the way to n is not? No? So it's some funny thing.
Well, I guess, really the answer is you do a sleight of hand and that you define a closed form to be whatever you can get your algorithm to do.
Yeah, no, I understand that, but I find it funny now that one pays attention to the summation having to be shortened in a shorter expression, but the products over the.
No,
Well-
it's a good question. It's even a reasonable point in that lots of sums, say in computer science, when you're analyzing the runtime of algorithms, turn out to involve harmonic numbers, which are definitely not closed form in the way that I've said here. But in a certain sense, a harmonic number is very much a closed form, and we understand them very well, exactly asymptotically. We know lots of identities about them, and that would not qualify as closed form in Gosper's algorithm.
Now, of course, also for n factorial, we have a pretty good asymptotic formula, right? So
yeah, that is true. That is true. And somehow, you can get a better handle on summing over n factorials than you can summing harmonic numbers.
Yeah, closed form is not well defined. I guess a better term will be a hypergeometric term. This is the
Yep.
Very good point. Yeah.
Anyway,
So
very
that
nice talk. Very nice talk.
Other question for Robert? Okay, one last question. So there's also something called Q series and Q Gosper. Do you think you might be able to get Q analogs of this beautiful theory?
That's a good question. You would need to sit down and take a look at. Yeah, because when you do Q analogs now, you don't have these actual polynomials, but you have these sort of formal power series you have to deal with. So you would need to think about this vector space instead of the normal polynomial vector space. I think it's possible, but I don't know off the top of my head.
Yeah, it'd be nice to see if there's something called Q Bell numbers. It'd be nice. I think it'd be a nice project. So instead of n factorial, you have a Q analog of n factorial, which is 1 times 1 plus Q times 1 plus Q
Yeah.
plus Q square. And there is a Q gospel. And I wonder if the Q Bell, some kind of Q analog of Bell will show up. Who knows?
Yeah, normally a lot of the Q theory sort of goes over as the normal theory does. So you would want to go look through the Q Gosper and make sure that the theory there works the same way. But then I think it might work. Yeah.
Any more questions for Robert? Well, thanks so much for coming. The next talk is in 2 weeks by Volodya Retach. I hope to see you there. Robert, please finish your talk. Thank you very much. Thanks so much for coming. What a great talk. Bye-bye. Thank you.
Bye, everyone.
Thank you.